this. Just as a reminder, in this lecture series, we already covered the introduction. That was the first chapter. The second chapter was the theorems and postulates. The third chapter is the variational method. With which we are nearly done. I'd like to wrap that up today and hopefully proceed then. Last week, you've already heard about perturbation theory. And chapter 5 is going to be on molecular quantum mechanics, or the molecular quantum theorems. And after that, we have chapter 6 on Huckel theory. Chapter 7 on Hartree-Fock. Chapter 8 on density functional theory. In chapter 9, we have correlated methods. Then we have some comments on basis sets and pseudopotentials. And then we have something called model chemistry. Now, this is a rather ambitious schedule. I believe I mentioned that already. Due to the Zoom lecturing, we do experience some delays. But the good news is that this is ordered in terms of importance also. So it is really very, very important for you that we cover at least this. And the exam will be biased towards these earlier chapters, okay? The later stuff is also, of course, highly relevant, but this typically constitutes a level of theory and depth where advanced textbooks and materials would begin with, okay? So if you cover these first 6 chapters, you have everything you need really to go beyond. So whatever we do in excess of Huckel theory will be, of course, highly desirable and beneficial, but it's not as crucial as the beginning of the earlier chapters. So last week, you basically crossed this off. This one we have already, this as well, and we will be finishing off the variational method today, and then hopefully move into chapter 5 on the molecular quantum mechanics. So as usual, please interrupt me if you have any questions or remarks here. So last time I talked to you, we had finalized the expressions for the variational method, and I'd like to ponder a little bit more on the linear algebra, the matrix kind of notation, which we've introduced in the end. So this is a subchapter 3, if you wish, and you can call it matrix notation. So as you remember, we had a set of equations, right? And this set could be written as a sum of an index k, which runs over the coefficients in our basis set expansion. So we approximated our trial wave function as something like this, all right? So going up to n basis functions. So we had this coefficient, and then it was multiplied with the Hamiltonian matrix element and energy W and the overlap integral. And each of these sums must be 0. And we had a set of those, right? So this was for all I equals 1, 2, and so on, n, right? So what this meant is that you can write this as, so it's identical, right, to writing it in matrix notation as this big matrix in brackets that gets multiplied with a C vector, right? And that must be equals 0. Okay. Now, let me remind you, right? We got the index k from our expansion, right? This is our first index. Then we have the second index. We have that index from the variational theorem, namely that we differentiated with respect to coefficient I, our energy, and this had to be 0. This gradient had to be 0. If you do this with respect to every derivative, that's how you get your second index, right? And now you recall that there's this important rule that for non-trivial solutions of this equation, the determinant of this thing, this bracket here, which you can also write like this. This determinant must also be 0. And that generates our third index, namely that because of this, we get a characteristic polynomial, also known as the secular equation. And from this, we get as many solutions as we have roots. And we have as many roots as we have terms, as we have rank here in this matrix, and that is your n, right? So again, you get n new solutions, and that is, so that means we have a set of C vectors for every solution. That's our third index, right? So first index is K, second index I, third index J. All right. So this just to recapitulate, and then we saw we can, because of this, we have a set of expressions. If we say if Sij Kronecker delta, right, only your H survives and you have your H matrix times the coefficient vector J equals the eigenvalue J times the coefficient. Right? And so we realize that this is an eigen equation, right? And this is the effective way to phrase within linear algebra Schrödinger's equation. So this is Schrödinger's equation in matrix notation. Now, you could solve this equation with common numerical methods, right? So this can be solved for large n, right, on computers. And this has, of course, then resulted in what we nowadays it has become a field of chemistry called computational chemistry. Now, there are obviously other applications of computers in chemistry, but this kind of problem, so solving Schrödinger's equation in some basis, right, with some Hamiltonians, they can be approximate. This is an important branch of computational chemistry. Oh, I have a comment in the chat. Yeah, my zeros look like Phis. That is true. I'll try to clarify this more. So my phi has a very vertical line, and my zero has a line that is more diagonal. Right? So I'll beg you to pay attention here. I'll try to make that clear. So if you have an equation like this, which you need to solve, then this can be quite costly if you use determinants. Solving the secular equation, so finding the roots, it scales factorially in n, right? That is, it scales as n factorial. If you instead diagonalize your matrices, then solving this equation is basically linear, and the diagonalization scales as n to the cube. Okay. So it should become clear to you that if you plot the cost of your calculation or the time you will need to obtain a solution for fixed hardware as a function of n, right, your factorial will increase incredibly fast, faster than exponential, right? While a cubic scaling is much more favorable. Right? So this is the reason why there's a lot of talk about diagonalization in chemistry. Now, we'd like to discuss this further. So, moreover, let's consider the following cases. Consider this. If your H is diagonal, that means basically that Hij equals Hii delta Ij, okay? This means that all cross basis functions, all integrals where basis functions come from different, where you have different basis functions, they don't contribute to the energy. Now, typically, this seems unreasonable, but you can imagine a situation. So, for example, there's a limit where this is true. Suppose that you have on every atom one basis function, right? One basis function f per atom, and suppose that these atoms are very far away from each other, so in the dissociative limit, right? And that atoms are far away. Well, then this would certainly be true, right? So this is, of course, not so useful for chemistry, since atoms are basically not interacting. Their basis functions are to dissociate, but it is important to consider such limits to see if they make sense, right? So this is a useful test to look at limits that are maybe less interesting to you, but that can help you to validate and verify your theory, right? And so you can gain confidence that your theory in these limits converges to what is right. So for this reason, this limit is not irrelevant, right? Now, what happens if that is true? Well, you know, our determinant must be 0. And we can, if we have a diagonal matrix, right, you can always add another diagonal matrix and it remains diagonal. So let's add this lambda identity, right? The identity is, so diagonal matrices can always be added. And that means that if it's only diagonal, that means you basically have here the product of your diagonal terms. Okay. And so the obvious solution to this is then that for every term, your lambda I is equals to this Hamiltonian element, right? So that's formally these eigenvalues would become your energies, right? So remember so we are basically writing this thing up here as lambda I, right? So that's what has happened here. So you want to solve for these energies, and these lambdas are simply your energies from each atom, right? Now, this is of course not always true. So let's consider the next case, namely if C is eigenvector of a matrix A, then if we multiply it with some constant, D times some constant, will also be an eigenvector of okay. And this means that we are free to select this constant such that our K, so we select K such that the norm of K, so the sum of our, we select our D, I don't know why I'm talking about D. Okay, we select our D such that the norm of D, so the di 2 over n, 1 over n equals 1, okay? This means D is normalized. Yeah. So we can simply impose that such that this is given, and it is also desirable if our eigenvectors are orthonormal. So what does that mean? That means it's the same as saying your B times C. So the inner product of two vectors would be the element-wise product of these two vectors must be 0. Okay. All right. There are orthogonalization procedures which can ensure that. And given all of that, we can now arrive at the following, we say there are n eigenvalue equations, right? Which again have this shape, right? Discussed this above. Where your third index goes from 1 to n. Where we now say, well, we can collect them all together in a single expression if we use for the eigenvalues the diagonal matrix W, which we define. We simply put the eigenvalues on the diagonal. Right. And everything else is 0. Okay. So this is a diagonal eigenvalue matrix, and with the coefficient matrix simply being defined as your coefficient vector 1, coefficient vector 2, and so on, coefficient vector j. Then we reach coefficient vector n, right? Which is also, so this is n times n, right? And this is n times n, since the coefficient vector has the length n. We can collapse the set of equations. So this yields the expression HC equals CW. Okay. So now instead of this ugly set, we can have a single expression here, and we can now say, well, first we are interested in these eigenvalues, okay? So if we multiply this with the inverse of the C matrix, and we multiply this from left, right? Then the C matrix in front of the W, right? So to solve for our W matrix, right? Then the C matrix in front of the W becomes identity, becomes 1, right? And so we have C inverse HC equals the W matrix. Okay. So far so good. That's nice. But now you can, as a next step, so this is an important equation. But now as a first step, we can say that one can show, we will not show this here, but you can show that also in practice, not generally, right? But in practice for our problems. So in practice, our C matrix happens to be such that the inverse is nothing else than its transpose. Okay. So C minus 1 equals C transpose. Okay. So this is due to the fact it follows from H being real and symmetric, which comes from H being resulting from a Hermitian operator. It's one of the consequences. It also requires your eigenvalues to be on this so with eigenvalues W being with Wi being the eigenvalues, excuse me, being eigenvalues of orthogonal C vectors. Okay. So this is we meet these conditions, and then you can do it like this, and from this follows that CT H C equals your diagonal matrix. What we don't know here, as always, right? Just a reminder, is the variational theorem. We know our basis, and we know these matrix elements. This is known, right? This is what we want. And this expression is the working horse for getting what we want by solving this expression by varying the C matrix. You can basically imagine this is just a matrix. It's basically your C matrix, right? Your C matrix, to transpose it is just a reflection, basically, right? You relabel the indices, right? So that's a trivial step. So you put some random numbers into your C matrix, and you shuffle them and change them until you get something diagonal, right? That's the numerical procedure. So you shuffle them, and you always multiply it with this H matrix, and you do this. So you sample. This means the computational algorithm simply needs to sample C and then evaluate the transpose, its product with H, right? Until it's diagonal. Right. So whatever algorithm you cook up here, it doesn't really matter. You can sample this C matrix until it's diagonal, and this, it turns out, is quite efficient computation. Right? It's much more efficient than solving the roots for the determinant in the secular equation. Right? So this is what scales cubically, and basically one way to think about it is that you could go ahead and ask yourself, well, each coefficient, I just try to change it such that the off-diagonal elements become zero, right? So, for example, by quenching all of diagonal elements. Until they are 0. The only condition which must be upheld is that you conserve the orthogonality, right? So while keeping Ci, Cj orthogonal. So this diagonalization is, of course, an old thing in applied mathematics, and there are tons of methods for doing this. If you want to program this yourself, you should do this. It's also a common question I ask in the exam. Please diagonalize a small matrix. When they are small, you can do this by hand. There is, so there's an old numerical problem, and you now understand how it is connected to solving Schrödinger's equation for actual molecules. Okay. You can look up solutions or suggestions how to solve this in the numerical recipes, which is a treasure which is available for free online, and there are methods such as the Givens method, the Householder method, and also the QR algorithm. If you're interested in these, you can program them yourself. This should also have been part of your introductory math lectures at the university if you took some. So this is really nothing special. Diagonalization is a very common numerical problem. And you've seen now how we can end up with this problem, starting out with quantum mechanics. All right, are there any questions at this point in time? This doesn't seem to be the case. I'd like to then just very briefly mention some alternatives to this diagonalization. So this is the last very short subchapter for alternatives. Alternative one is that you minimize W with under boundary condition that your wave function must be 1, right? And it remains normalized, right? So this such a boundary condition means that we can use a technique well established also from constrained minimization. There's a constrained minimization problem. So a common example is if you imagine a cone which lives in 2D, and you're interested in the minimum in this cone, but you have some constraint, right? So not the global solution, but the unconstrained solution, but maybe this axis here. So let's say this is X and Y, and this is your energy, for instance. Let's say your X value is not free for you. Right? And so you have to do your optimization at some X value, right? And so all of a sudden, it's really where you have to optimize is this plane here, which goes up here, right? And so this is your solution to your constraint optimization, and not the global optimum, right? Now, the technique that is typically used for this is called the Lagrange multiplier. So Lagrange was one of these famous French mathematicians and physicists whose name is on the Eiffel Tower in Paris. So next time you visit there, make sure you'll have a look at it. The way to phrase things is within a Lagrange multiplier based constraint minimization would be to write your energy as a function of this multiplier, and you have your typical expression, right? That's what you would minimize, and then you add to it the condition, and the condition is that 1 minus this must be 0, right? So you add a 0 in front of it, right? And in front of this condition, you have the Lagrange multiplier lambda. You then do whatever you wanted to do, for instance, differentiate with respect to your coefficient. And now you inherit an additional term which contains this lambda, right? So in particular, in this case, what you have here is your DCI, and then the double sum. You do the usual basis expansion. Right, that will be your first term. And you get the second term when you differentiate lambda times 1, of course, this is just 0, but you get a second term for this overlap integral. Right. And now you already might remember from our differentiation in the beginning when we derived our system of equations, it looked awfully similar, right? We went through a much more lengthy derivation, and you see with this simple Lagrange multiplier trick, we can do this quite efficiently. And this of course results in what you know already. So it's still this one. So CK HIK minus lambda sum over K CK SIK. And so if you factor out your expression here, you see now that instead of the W, we simply have the lambda. And so this results in H minus lambda S C being 0. Okay. So you recover the same kind of, and now we can use the secular equation and so on and so forth, right? It's just that this lambda, this Lagrange multiplier, you realize it's nothing else than the energies, the eigenvalues, right? So the Lagrange multiplier becomes the energies. Okay. So for any one of these energy eigenvalues, the Lagrange multiplier would allow you to get the minimum, the constraint minimum. The second alternative is using this projection trick. And so let's write our Schrödinger equation and use projection trick. So if we expand in our basis, then we can see that on the left side we can let the operator get into the basis, into the summation. So you have wait. Before we do this, now we did the expansion and now we project. Project onto Fj, right? So we apply Fj on the left, and we do this for all k. So what you get then is your summation Ck d tau Fj h Fk equals equals Ck d tau Fj Fk. And this is our matrix element Jk, and this is our matrix element Sjk. And so what's written here is Ck Hjk equals Ck Sjk times the energy. And if you pull one over and factor out, again, you get the expression we by now are all familiar with, which leads to your secular equation. Okay, so this is just to show you, right, that there are many ways how you can end up in Rome. We discussed step by step, slow way, right, but very detailed. So you have a really you can follow in detail, but you see also it can be very instructive and fascinating to arrive at the same result with slightly different notations. These are all equivalent and equally true, and they make use of so this projection trick, something we discussed already in the second chapter. It's quite common to use this in practice because it's more efficient, right, or faster. same holds for the Lagrange minimization. We discussed the role of diagonalization. I hope you could follow that. With all of this, I'd like to conclude now this subchapter. You've had perturbation theory last week, so we're going to jump ahead in the second lecture, in the second hour today, and tackle chapter 5 on the molecular quantum theorems. All right, it's 11:06. Let's have a break and we reconvene at 11:20 for the second part of today's lecture. Okay, let's continue with the theorems in molecular quantum mechanics. Which constitutes the fifth chapter in this course. So in this chapter, we'll discuss 4 subtopics. The first one will be on the electron density. The second one will be on the dipole moment. And polarizability. The third one will deal with the virial theorem. And the fourth will discuss the chemical bond. Again, as you might have realized already, we go pretty deep in terms of underlying theory and mathematics, and things might appear abstract, but I hope we do succeed in connecting things to the actual chemistry, that you realize that at least these things explain and rationalize what chemistry is all about. So for this reason, the fourth subchapter, the chemical bond, is obviously at the heart of the chemist's interest, while naively or on first sight you might think we don't need quantum mechanics, we don't need electrons, we can just work with the bonds. This is how we can explain how chemical bonds come about. All right. So in this chapter, we will try to connect to some more realistic concepts which you might encounter in daily life in terms of being a chemist. And we'll start out with the electron density. Which is a concept which we would like to formalize in terms of the probability discussions which we've had surrounding Born's rule. right? So what we are talking about is a probability to encounter electron in some volume element dV with some spin, right? So you could also include some spin component with this, right? But we'll skip that for now. And so what you should imagine is spatial coordinate frame, right? That's the 3D space. And in here, we consider now a volume somewhere, okay? Suppose here. And we consider now this volume, this little box here somewhere, okay? So this is our box dV, which you somehow carved out in space. And you can imagine, of course, dV means dx, dy, dz. You can imagine that this should become arbitrarily small, of course, right? So the smaller you make that, the finer your resolution, right? So arbitrarily small. Now, things should be so small, right? The grid you span should be so small, so fine, that the properties of interest, let's say your dipole moment, let's say your energy, that they don't change anymore. Right? If you go beyond, then you're wasting resources. If you're too coarse such that they still change, then you're in an unconverged regime. You want to converge your grid and your resolution. So resolution or grid needs to be converged with respect to your observable of interest, right? We saw that in the discussion of the convergence of the energy and some tri-function and the wave function, and the energy converges faster, right? So it could be that one observable converges faster than the other. So it depends, right? Okay, so we partition space into these little volume elements, and we ask the question, what is the probability to find our function here? So we have the electronic wave function in tau, right? Is a wave function. It's some function. It's the identity that depends on each of your variables, right? For n electrons, let's say, and each one has a spin too. Okay. So it's this beast of a function, right? And you're asking this question, what is the probability to get just one electron, right? So if we ask for this probability, we need to square this. So a probability to encounter electron in here, right? We need this probability from this wave function, right? This is, there's some analogy to humidity in a cloud. Okay, so as you imagine, you transpass a cloud, right? The air is covering the space, and there can be more or less humidity in the air depending on where you are, right? And that can change greatly, right? Outside the cloud, you have no humidity or very low humidity, and then you go slowly inside, and as you come to the center, right, you'll be wet in no time. And so in this sense, you should think about the electron density, right? Outside your molecules, there's not much electron density, and as you go inside, there's more and more. So this probability we know is the square. This is Born's rule. This probability in tau would be something like this, d tau, right? And so that is the probability to encounter an electron probability to encounter simultaneously E1 with MS1 in dx dz dy equals dv1, okay? E2 with MS2 in dv2, and so on, until En with MSN in dvn. Now that sounds terrible, right? So you have small volume elements all over the place, right? And to simultaneously encounter each these electrons in either one of those, this would be given by this product. But we can simplify this expression. So one thing is we can assume closed spin shells, and that means what this does is that your sum over possible spin states, you're basically fixing this, right? This sum simply becomes the sum over total spin psi squared. And what we'd like to do now is to consider just one electron, right? So Born's rule is for all electrons, right? This is simultaneously, right? Now consider only one electron. What happens? Well, so this means we can integrate out all other degrees of freedom, right? They don't matter. We only look at this one electron. So this means we can use the sum over our spins, and then we go over dv2, dv3, and so on until dvn psi. And here we have, for the one we are considering, dx1, dy1, dz1. So that's our dv1. Okay. Now, because electrons are not distinguishable, right? This is, so this is, you have this n times, this exists n times, since electrons are indistinguishable. So this means that we have an n times spins over dv2, dv3 till dvn psi, and this is what we call our electron density at x1, x2, x3, y1, z1. Okay. So you integrated out the spin information, you integrated out all the spatial information of all other electrons, and you are asking, what is this one, for one electron, the one electron density? Right. So if you integrate now over x and y and z, this row, right? Where I will remove now the indices, because it's just one out of the indistinguishable set of n electrons. So this is just the same for every electron, which is why we have this n here, and which means that if you integrate the whole thing, you need to recover your total number of electrons. Right? So this is how, from the Born's argument and arguing with the indistinguishability of the electrons, you can arrive at the expression or at the definition of the electron density. And this is an actual observable. You will encounter rho in X-rays and atomic force microscopy, and scanning tunneling microscopy, and also in transmission electron microscopy. Okay. These are all direct experimental measurements of the electron density. Now, the electron density is an intuitive concept, right? And we'd like to discuss a couple of properties it has. And one of them is that, of course, you do have something as atoms come together, the atomic picture of the electron and the orbitals and the shell structure, let's say, this picture gets slightly distorted, but it is still something we appreciate, right? And so it is natural to ask how do we recover the full electron density from molecular orbitals and individual electron behavior. Now, this means that rho within molecular orbital, that means one electron per orbital, right? Or two, depending on occupation numbers. So NJ electrons per orbital theory is simply rho of R. So everywhere in your space, mind you, in this box, right? Anywhere in space, you have such a box, right? You can ask, okay, in this box, what is the value of my density, right? That's what this R means. So this rho of R is simply the sum over your orbitals squared, J, times the occupation number, right? Only occupied orbitals contribute to the electron density, right? So, that is, of course, then if you integrate the whole thing, you should also recover the number of electrons, right? So that's how you can think about it. And this is also known as the orbital density, right? The individual electron density. So one orbital, you simply square it and you get that density. Now, what does this mean? You can simply draw a picture for your atom. Let's say you have an atom with a nuclear charge, some number, doesn't matter. And so in this axis, we have charges, right? This is the proton number. Nuclear charge. This number of protons, okay? And here you have space, so let's say X. And now you can ask around this free atom, how does the electron density go? And what you have is, for instance, your S orbitals might look something like this. Think of the hydrogenic solution of the Schrödinger equation. It's an exponentially decaying function. You square that, so you have e to the -2 times r. And so that would be simply your s orbital, okay? And on top of that, you now have a shell electron. So this could be your phi 1s, for instance, squared. And then you have, now note that at the nucleus, it's really your 1s that dominates things. So this could be your phi 2s squared, right? So something like the beryllium atom might just look like this. So the whole thing, right, this is your rho as a function of x. So you see a very natural, the orbitals, you just sum their square up and you recover the electron density. The electron density has an important relationship to the wave function. Right? So you remember from our first postulate that the system is represented by the wave function. Now, one of the later chapters in this course is density functional theory. And density functional theory works only with the electron density, as we just introduced it. Now, how is that possible? Are we allowed to do this? Is rho, does rho, the electron density, represent your system just as well as the wave function? Now this is not an obvious thing, and I'd like to tell you about two ways to convince yourself that this is okay. Right? So rho is in a 1-to-1 relationship with psi, and so first postulate of QM also holds for rho. Now, the first way to see this is through what is known as the Homeback-Kohn theory. Homeback-Kohn theory. Now, the Homeback-Kohn theorem uses a proof that is known as reductio ad absurdum. Okay, it's fairly simple. We presume the opposite of what we think we will prove. Okay, so we will presume that psi and rho are not in a 1-to-1 relationship. Right? So in other words, that two different psi's could map towards the same electron density. Now that would not be possible if the electron density is in a 1-to-1 relationship with the wave function. Right? So let's write this down. This would mean that if we consider a Hamiltonian of some system and some wave function psi1, right, we could write this Hamiltonian as this wave function with the kinetic part, the kinetic electron-electron interaction, the potential electron-electron interaction, and the external potential. Yeah. And we can do the same for a second wave function. Now, the second wave function, the first Hamiltonian has an external potential 1, okay, system 1. In the second wave function, this is not the optimal wave function. This is just some other trial wave function. Imagine, for instance, you have the Hamiltonian for the molecule water, and then psi1 is the wave function of water, and psi2 is the wave function, let's say, of ammonia. So we plug in this wave function and we calculate again the expectation value with the electron-electron operators are the same. Let me put some hat here. But the external potential now is the one of system 1. So the one of water, now evaluated with the wave function of ammonia. Now, by virtue of the variational principle, we know that if you use some trial wave function, which is not optimal for your system, your expectation value will be above, okay? So we have an inequality between these two. All right. Now, obviously, we can write these two expectation values. Simply, let's call this here a universal electron-electron operator. Let's call it FEE. Okay. So then we can write psi1 operating with FEE. I'll drop the EE altogether. It's just the electronic. It's a universal operator F on the electron, right? Plus psi1, the external one. Psi1. So this must be smaller than me doing the same here on the other side. Okay. So that is the same. Let me equation here. Yeah. And now we make the absurd assumption, right? No, we suppose the opposite of what we want to show. Suppose opposite holds true. That is that psi 2 maps to, if I square psi 2, I get the same electron density as I would get from psi 1. Okay. Well, if that is true, the expectation value with our external potential must be the same, right? So then I would have on the left psi 1 F, psi 1 plus external potential is just a multiplicative potential. So I have here the electron density to which my psi 1 maps times my external potential. And this should be smaller than psi 2 F psi 2 plus the same term. This is just a function, right? Now I'm a bit sloppy here. So this is over the full space, okay? Now, these two integrals are the same, right, in this inequality. So I can cancel them. Okay. And what we are left with is psi 1 F psi 1 must be smaller than psi 2 F psi 2. Okay. So we've done this now for our first system. Now let's repeat this exercise for the second system. Now we go for H2. right? And we would use psi1 h. So again, we would have F plus V2 external potential. Right. And on this side, we would have psi2 F plus the external potential 2. Okay, so now the wave function on the right is the appropriate, the function that minimizes your energy. So your right-hand side expectation value must be smaller than your left-hand side, right? So your inequality sign is in the other direction. And I can, with the same assumption that the two wave functions map towards the same electron density, I arrive at this expression where now psi1 F, psi1 must be larger than psi2 F, psi2. Right? So these two inequalities obviously conflict with each other. You can also make this even more explicit. So you can flip this around. Psi2 F, psi2 is smaller than psi1 F, psi1. And if I now add these two inequalities, I get psi1 F psi1 plus psi2 F psi2 is smaller than psi2 F psi2 plus psi1 F psi1. In other words, A plus B is supposed to be smaller than B plus A, which is absurd, right? So because this leads to an absurd result, we conclude that our assumption that the two wave functions map towards the same density is not possible, right? So assumption leads to absurd result opposite it must hold. That is, any wave function I of some system maps to its own electron density I in a one-to-one mapping, right? It's bijective. All right, so this is a formal proof. Another way to see this is by virtue of something which is known also as Kato's Cusp theorem. So this is one way to see this. Let's call it I. The second one also Kato's Cusp. Now, Kato's theorem says that it's basically a differential equation of first order, where you say that the derivative with respect of your electron density with respect to the distance R So R equals. So as this distance becomes 0, what you get is minus 2 nuclear charge divided by the Bohr radius times the electron density. So it's like an eigenvalue expression too, right? Yeah. So this is your eigenvalue. That's how you can see it. But what you see here is that as you go through space, right? An electron density that goes as e to the minus z r, right, meets this condition, right? So you have in this gradient, you have the nuclear charge encoded here, right? So as you walk through space and you watch the gradient of your cusp, you can infer the nuclear, you infer the cusp, so that means you have an atomic coordinate, and you infer the nuclear charge I from the cusp condition, and this set determines your external potential. Which you do for every atom, Zi is R minus Ri. Okay, and the external potential determines your Hamiltonian and thereby the wave function through Schrödinger's equation. Okay. So this is a less formal proof, but you also see that for any external potential, there will be only one wave function then. And you get that external potential from considering your electron density only. Okay, are there any questions? If not, it's already noon. So I'd like to thank you for your attention, and I'll see you tomorrow. We continue this discussion tomorrow. Bye-bye.